Welcome to the 39th lecture in this open course on diffusion in multi-component solids. In this lecture, I shall discuss the derivation of expression for the diffusion flux of a component in terms of chemical potential gradients. We will see that for the substitutional diffusion by vacancy mechanism, the flux of a component depends not only on its own chemical potential gradient, but also on the chemical potential gradients of other diffusing components. It is said that gradient in chemical potentials is the fundamental driving force for diffusion. Today we will see why it is so. We will try to derive the expression for diffusion flux under the chemical potential gradients. We will use the simple kinetic theory for this derivation. This type of equation has been derived long back by Seitz, Fischer, Holloman, Turnbull and by Bardeen. I will try to explain this theory in today's conventional terms. We have seen the expression for diffusivity d equal to 1/6 gamma lambda square, in which gamma is the successful jump frequency of an average atom and lambda is the jump distance. Jump frequency term gamma involves two types of contributions. One is the number of times an atom has energy equal to or greater than the activation energy for migration, and second, the probability that an adjacent site is vacant. So that belongs to the activation barrier for vacancy formation. In the absence of any driving force, we have seen at their regular atomic positions, the atoms are lying in a potential energy well. So if this is an atom A and it jumps onto the next site, it is called this V, there is no net change in the Gibbs free energy because of this jump. But in order for this jump to occur, the atom has to cross this energy barrier, which is known as activation energy for migration, delta Gm. When there is a driving force present, the situation is little bit different. Whenever there is a driving force, the jumps are biased in a particular direction, because if the atom jumps in that particular direction, it causes decrease in Gibbs free energy. So the first one, this diagram we have shown for the condition in absence of any driving force. We will see in presence of driving force, this potential energy well configuration is little bit different. Okay. So this potential energy wells would look something like this. So there is a driving force in the x direction, let us say. So when the atom jumps from this position into the next site here, we will see that it is associated with decrease in Gibbs free energy, and the decrease in Gibbs free energy is referred to as the driving force. So obviously we can see for the forward jump for our class here, let us call the jumps from left to right as forward jump and the jumps from right to left as reverse jump of the atom. So for the forward jump, we can see the atom has to cross a lesser energy barrier than a reverse jump. So for example, if the atom in this position wants to jump back, it has to cross a bigger activation barrier than for the forward jump. And because of the symmetric condition, we can show that the activation barrier for the forward jump can be written as delta Gm minus f by 2, and the activation barrier for reverse jump would be delta Gm plus f by 2. Now, if we denote the number of times an average atom has an energy equal to or greater than the activation energy for migration per second as gamma A, let us call it the jump frequency of atom. This is in absence of driving force, and this is only the migration part. So, as you see, the actual jump frequency gamma will have the migration part as well as the vacancy formation part. So, in my notation here, gamma A is the jump frequency which includes only the migration part, and gamma A is in the absence of any driving force. So, obviously, when there is a driving force present, like here, the forward jump frequency, let us call it gamma plus, will be different than the reverse jump frequency, let us call it gamma minus. So, in the absence of driving force, gamma A will be given as gamma A equal to nu 0 exponential minus delta Gm by kT, where nu 0 is the Debye frequency, the number of time atom vibrates per second. So, obviously, gamma plus would be given by nu 0 exponential minus delta Gm minus f by 2 by kT, and gamma minus would be nu 0 exponential minus delta Gm plus f by 2 over kT. So, we can write this exponential term as exponential minus delta Gm by kT times exponential f over 2 kT. So, obviously, gamma plus would be equal to gamma A exponential f over 2 kT, and gamma minus would be gamma A exponential minus f over 2 kT. So, gamma A here again represents the jump frequency of atom A in absence of any driving force. So, the jump frequencies in the forward and reverse direction will be modified by this driving force F, and the driving force is usually a positive quantity, and so F will be given as minus delta G. So, delta G is the difference between the Gibbs free energy of this site and this site, and it will include only the non-ideal part. So, we will come back to it later. So, with this we can use an approximation. Exponential x is approximately 1 plus x if x is much less than unity. Now, in these expressions for gamma plus and gamma minus, f is usually much less than kT, and so we can use this approximation and we can write gamma plus is equal to gamma A times 1 plus f over 2 kT, and gamma minus is equal to gamma A times 1 minus f over 2 kT, and the difference between the forward and reverse jump frequencies would be gamma plus minus gamma minus should be equal to gamma A times f over kT. So, it will be clear why we got the expression for the difference between gamma plus and gamma minus as we proceed. So, we have now expressed the forward and reverse jump frequencies in terms of the driving force and the jump frequency in absence of the driving force. Now, let us try to evaluate the diffusion fluxes in terms of these jump frequencies. So, if we consider two atomic planes, let us plane 1 and plane 2, and the distance between the two planes is lambda. So, each plane can be thought of as surrounded by an element of volume lambda if we consider unit cross sectional area. So, this is basically lambda. Let us say the number of atoms of A on plane 1 are Na, and the concentration of the volume element around plane 1 is Ca, and so we know Na is equal to volume is lambda times Ca. And if we consider that there is a concentration gradient from plane 1 to plane 2, then the number of atoms on plane 2 would be Na plus lambda times dou Na by dou x, that is the gradient of number of atoms with respect to x. And so, in terms of Ca, it can be written as lambda times Ca plus lambda square dou Ca by dou x. Now, we will be treating here the diffusion that occurs by vacancy mechanism. So, it is important to know the vacancy concentrations on the two planes. So, if we express the vacancy concentration of plane 1 as x1v, and there is also a gradient in vacancy concentration. If we allow for the gradient in vacancy concentration, the vacancy concentration on plane 2 would be x1v plus lambda times the gradient in x1v with respect to x. Now, with this, if we want to evaluate the interdiffusion flux across a plane that lies in the middle of plane 1 and plane 2, we need to consider how many atoms are jumping from plane 1 to plane 2 per unit times, and how many atoms are jumping from plane 2 to plane 1 per unit time, and take the difference of the two. So, the difference will give me how many atoms of A are crossing this plane at the middle per unit time, per unit cross sectional area. So, that is the diffusion flux across this plane in the middle of plane 1 and plane 2. So, if I denote the number of atoms jumping from plane 1 to plane 2 per unit time as J A 1 to 2, that would be equal to the jump frequency of atoms A, and this I am considering again including only the migration part, times once the atom has the required energy to jump, the next side also has to be vacant. So, this will also depend upon the probability that a vacancy exists on the adjacent site. So, it depends upon the vacancy concentration on plane 2 here. So, x1v, this is at plane 2, times the number of atoms of A on plane 1. So, this would be equal to gamma A plus times the vacancy concentration on plane 2 is given by this term. This will be x1v plus lambda dou x1v by dou x times the number of atoms of A on plane 1 is lambda Ca. So, this is J A from plane 1 to plane 2. Similarly, J A from plane 2 to plane 1 would be given by the jump frequency of atoms A, and this will be the reverse jump frequency, which is gamma A minus times the vacancy concentration on plane 1, which is x1v, times the number of atoms on plane 2, which is lambda Ca plus lambda square times dou Ca by dou x. And so the interdiffusion flux Ja is given by the difference between 1 and 2. So if we take Ja as Ja1 to 2 minus Ja2 to 1, if we arrange the terms containing lambda square together, we will get lambda square times gamma A plus Ca dou x1v by dou x minus gamma A minus x1v times dou Ca by dou x plus gamma A plus minus gamma A minus times gamma A plus x1v lambda Ca x1v times Ca times lambda. So now it will be clear why we evaluated the difference between gamma A plus and gamma A minus. Let us denote this as equation 3. So if we now substitute for gamma A plus, gamma A minus, and for the difference between gamma A plus and gamma A minus from these equations here, we will get Ja equal to gamma A lambda square into 1 plus f over 2 kt times Ca dou x1v by dou x minus 1 minus f over 2 kt times x1v dou Ca by dou x plus gamma A times f over kt times x1v times Ca times lambda. Let's call this equation 4. So we have got the equation for diffusion flux of A in terms of the driving force F and the jump frequency gamma A in the absence of driving force, and the gradient of vacancy concentration as well as the vacancy concentration, and lambda the jump length. So this will be true for any type of driving force, and the specific expression we will try to derive for a driving force, which is the chemical potential gradient. So let us try to see what form the driving force F takes when there is a chemical potential gradient. For this, let us go back to this diagram of plane 1 and plane 2 here. When an atom A jumps from plane 1 to plane 2, what is happening is the number of atoms of A on plane 2 have increased by 1, whereas the number of vacancies on plane 2 have decreased by 1, and the reverse has occurred in plane 1, that is, and the number of atoms of A on plane 1 has decreased by 1, and the number of vacancies on plane 1 has increased by 1. And we know the increase in Gibbs free energy when an atom is added to a homogeneous alloy is the chemical potential of the atom. We can similarly define the chemical potential of a vacancy. It is the change in Gibbs free energy when an atom is removed from the interior and placed onto the surface, in which process one extra lattice site has been created. So if there is a chemical potential gradient, suppose let us say chemical potential of A is decreasing from plane 1 to plane 2, obviously there will be a net decrease in Gibbs free energy, and this will act as a driving force for diffusion from plane 1 to plane 2. So, if we consider a binary alloy of A and B, and since we are considering the diffusion by vacancy mechanism, let us also consider vacancy as one more species which is diffusing. This is because by creation or destruction of vacancies, there is a change in number of lattice sites, and so we need to consider vacancy as one more species here. So, we can write the total number on any plane of lattice sites as n equal to Na plus Nb plus Nv, and the Gibbs free energy of this plane can be expressed as G equal to mu A Na plus mu B Nb plus mu V Nv. Now, G can also be expressed as, for any homogeneous alloy, as G0 plus Gxs minus T delta Sm ideal. So, in this expression, G0 is the Gibbs free energy before mixing. This part represents the change in Gibbs free energy if the mixing was ideal, that is, this part is related to the change in configurational entropy because of mixing, and Gxs is the excess Gibbs free energy, which is basically the change in Gibbs free energy because of all the other reasons than this ideal configurational entropy change. Now, when atom is jumping from 1 to 2, the driving force associated with this jump will be related to the change in Gibbs free energy only because of the non-ideal part, and so we can write the change in Gibbs free energy as the atom of A jumps from 1 to 2 as delta G is equal to dou Gxs by dou Na minus dou Gxs by dou Nv on plane at x plus lambda minus dou Gxs by dou Na minus dou Gxs by dou Nv at the plane x. Now, this term dou Gxs by dou Na denotes the change in excess Gibbs free energy because of addition of one atom of A, whereas this term dou Gxs by dou Nv denotes the change in Gibbs free energy because of addition of one vacancy, and since the vacancy is jumping away from the plane at x plus lambda, that is from plane 2 here, there is a negative sign attached to it, and this total expression we can write as lambda times dou by dou x of this difference between dou Gxs by dou Na and dou Gxs by dou Nv. And since f is simply minus delta G, we get the expression for f as f is equal to minus lambda dou by dou x of dou Gxs by dou Na minus dou Gxs by dou Nv. Now, if we substitute for f from this equation, let us call this as equation 5 into equation 4 here, it will be a long expression, but we can approximately neglect any term in lambda which is greater than lambda square. Now, since the term f involves a term lambda, so we can see here, and there is a term lambda square outside the bracket here, so lambda square times f will involve a term in lambda cube which we will neglect, and so this expression can be rewritten as Ja equal to gamma A lambda square times Ca dou x1v by dou x minus x1b dou Ca by dou x. F here can be written as minus gamma A x1v Ca lambda square into 1 by kt times dou by dou x of dou gxs by dou Na minus dou gxs by dou nv let's call this equation 6. Now we can write this dou x1v by dou x term as x1v times dou ln of x1v by dou x, and similarly this term, second term, we can write as Ca times dou ln Ca by dou x. So we have the coefficient of Ca times x1v here and Ca times x1v again here, and so this whole term we can take out. We can denote it as gamma A times x1v lambda square Ca times dou ln x1v by dou x minus dou ln Ca by dou x. This one we can write as minus 1 by kt dou by dou x of dou gxs by dou Na minus dou gxs by dou nv. Let's denote this as equation 7. Now let's try to find out the nature of dou gxs by dou Na and dou gxs by dou nv. Now from this equation we can write G as G0 plus Gxs minus delta Sm id can be written as T into K ln omega, and we know for the mixing of A, B and vacancies we can write ln omega as ln of total number of atoms n factorial divided by Na factorial times Nb factorial times Nv factorial. This we have derived when we went over the statistical model of mixing during our thermodynamic refresher. So this can be written simply as n ln n minus Na ln Na minus Nb ln Nb minus Nv ln Nv. Now if we take the derivative of G with respect to Na, which we know by definition is the chemical potential of mu A, which should be on the right hand side here. G0 is constant, so dou G0 by dou Na is 0. So we have the term dou Gxs by dou Na minus kt times dou ln omega by dou Na. So if I now look into this, if I take the derivative of ln omega with respect to Na, similarly dou Na by dou Na is 1 and Nb and Nv are independent of Na, so that the derivative of Nb and Nv with respect to Na would be 0. So we can write this as ln n minus ln Na, and if we take the minus sign out, and we know Na by n is the mole fraction of A or the atom fraction of A, which is denoted as Xa, so this will be equal to minus ln Xa, and so we get the expression for mu A as dou Gxs by dou Na plus kt ln XA. XA is the mole fraction of A. With a similar logic, we can write mu V equal to dou G XS by dou NV plus KT ln of X1V. X1V is the side fraction of vacancies. And from here, if we substitute for dou G XS by dou NA and dou G XS by dou NV into equation 7 here, we will get JA equal to gamma A X1V lambda square CA times dou ln X1V by dou X minus dou ln CA by dou X minus 1 over KT times dou by dou X of dou G XS by dou NA is mu A minus KT ln XA, and dou G XS by dou NV is mu V minus KT ln X1V. So this would be minus mu V plus KT ln X1V. Now this KT and KT will get cancelled, and so dou ln X1V by dou X will get cancelled with this term, and so we get the expression for JA as JA equal to, if we take the mu A minus mu V term together, we will get minus gamma A X1V lambda square CA times 1 by KT dou by dou X of mu A minus mu V plus gamma A X1V lambda square CA times dou ln XA by dou X minus dou ln CA by dou X. Now we know the mole fraction XA is given as the concentration CA times the molar volume Vm and so if we substitute here dou ln XA, dou ln CA by dou X terms will get cancelled, and so we are left with the gradient of ln Vm with respect to X. And so finally we get the expression for JA under chemical potential gradient as Ka is equal to minus gamma A X1V lambda square Ca times 1 by KT dou mu A minus mu V by dou X plus gamma A X1V lambda square Ca dou ln Vm by dou X. So this is the general expression for interdiffusion flux under chemical potential gradient. You can see there are three contributions here. One is from the chemical potential gradient of A, also the chemical potential gradient of vacancy, and also from the change in molar volume with X, and the molar volume will change with X if the molar volume is a function of composition, because the composition is changing with X. So the first two terms here are basically the Fickian flux, the flux because of the chemical potential gradients, and the third term here is the drift term associated with the change in molar volume. Obviously, if the molar volume will change with composition, there will be a volume flow associated with the diffusion process, and it will give rise to a drift, and so there will be a contribution from drift to the diffusion flux of A. Now if we assume that the vacancy equilibrium is quickly attained at every plane, that means if there is no excess vacancy flow, then the chemical potential of vacancy is 0. and then the only contribution will be from the chemical potential gradient of A and the molar volume change. In addition, if Vm is assumed to be independent of composition, and the only contribution will be from chemical potential gradient of A. So we can write Ja equal to minus gamma A x1V lambda square Ca times 1 by Kt dou mu A by dou x, and we can write this as minus La dou mu A by dou x. So we have derived the equation for diffusion flux of A in terms of the chemical potential gradient of A, and it is related to the chemical potential gradient of A through this term La. This is similar phenomenological type of equation that we used for flux as a function of concentration gradient, which were related through the interdiffusivity term. So more fundamentally, the diffusion is driven by the chemical potential gradient. Now this term La, which is called kinetic coefficient, we can see if we equate these two sides, La is equal to gamma A x1V lambda square Ca times 1 over Kt. And if we look at this gamma A x1V lambda square, this is nothing but the gamma lambda square, and if we add the geometric factor corresponding to the specific type of lattice, so for cubic this geometric factor is usually 1/6, so 1/6 gamma lambda square, and we know this is the Einstein's diffusivity, or which we call as tracer diffusivity. So we can write this as La is equal to dA star times Ca over Kt, where dA star is the tracer diffusivity, and this tracer diffusivity we know is essentially under negligible concentration gradient. So when there is no concentration gradient or negligible concentration gradient, we are talking about the self or impurity diffusivity, which is denoted by dA star. It is referred to as tracer diffusivity. So we can express the kinetic coefficient in terms of the tracer diffusivity of the particular atom. Now let us look into more general case when there is a net vacancy flow which is existing, which is bound to happen if dA star is not equal to dB star. dB star is the tracer diffusivity of B. In that case, we have to consider dou mu V by dou x term also. Now we know by Gibbs-Duhem equation xa dou mu A by dou x plus xb dou mu B by dou x plus x1V dou mu V by dou x should be equal to 0, and so we can express the chemical potential gradient of vacancy in terms of the chemical potential gradients of A and B. So that would be dou mu V by dou x should be equal to minus xa over x1V dou mu A by dou x minus xb over x1V dou mu B by dou x. And if we substitute for dou mu V by dou x from here into this expression for Ja, and neglecting the dependence of molar volume on composition, we will get the equation of the sort Ja is equal to minus La times dou mu A by dou x plus xa over x1V dou mu A by dou x plus xb over x1V dou mu b by dou x. And so Ja can be expressed as a function of chemical potential gradients of both the components A and B. It will be minus La times 1 plus xa over x 1v dou mu a by dou x minus La times xb over x 1v dou mu b by dou x. And so we can in general express this as Ja equal to minus Laa dou mu a by dou x minus Lab dou mu b by dou x. So the diffusion flux of A will be guided by chemical potential gradients of both A as well as B. The relation with chemical potential gradient of A would be expressed through this main kinetic coefficient Laa, and the contribution from the chemical potential gradient of B will be expressed through this cross kinetic coefficient Lab, and this will be true whenever the vacancy diffusion is involved, or whenever we are considering the substitutional diffusion by vacancy mechanism, because to more or less extent there will always be a net vacancy flow as long as dA star is not equal to dB star. Only the relative contributions will keep changing depending upon the difference between dA star and dB star. Now we did this for binary, but this is in general true for an n component system. So in general we can express the diffusion of a component I Ji as minus summation of Lij dou mu j by dou x, and j here varies from 1 to n. So we have obtained the Onsager's relation for diffusion under chemical potential gradient here. So it is important to note here, as long as the vacancy mechanism is involved, in order to define diffusion flux we need both the main kinetic coefficient similar to Laa here, as well as the cross kinetic coefficient Lij when I is not equal to j, similar to Lab here. One more point that I would like you to note here is that the dependence of molar volume on composition will also give rise to a contribution to the flux of A, and it comes through this term dou ln Vm by dou x. So only when we assume that the molar volume is independent of composition, we can ignore the drift associated with the diffusion, and that's why we define the volume fixed frame of reference. Alright, so we derived the relation that expresses the diffusion flux of a component in terms of its own chemical potential gradient, and when there is a net vacancy flow, that is when there is a difference in the tracer diffusivities of different diffusing species, then the contribution will also come from the chemical potential gradients of other components, and in general the flux can be expressed by this Onsager type of relation. Thank you.